How about d dx of just plain old secant x?
Secant tangent.
Secant x tangent x. That's what it was, right? So the derivative of plain old secant x is secant x tangent x. Now, applying the generalized derivative formula to this, if we want to find the derivative of secant u with respect to x, now we have to imagine u could be any expression with x's in it. It might be x cubed. Right? U could equal x cubed. It could be an expression with x's in it. How would we go about this? Well, the derivative, in this case, secant is the outside function. So what we would say is it would be secant u tangent u times the derivative of u with respect to x. Put a dot there. I don't know if a dot with or without the dot is the indication of multiplication. Chain rule says multiply by the derivative of what's inside the parentheses, and although the parentheses aren't all that prominent, there are implied parentheses around the u there. So we have to multiply by the derivative of u. So the derivative of the secant of something is secant of that something times tangent of that something times the derivative of that something. That's how we do that. So this is going to be secant of x cubed times the tangent of x cubed times the derivative of x cubed. Well, easy enough, 3x squared, right? So secant x cubed tangent x cubed times 3x squared, and probably the 3x squared should go in front. Just so there's no confusion, we're taking the tangent of what? We're taking the tangent of just x cubed. If I shove the 3x squared up next to that, that could confuse things. So 3x squared secant x cubed tangent x cubed. If we didn't have the chain rule to tell us what to do, probably we'd have left off the 3x squared. But chain rule says multiply by the derivative of that u there. Now, example 5. I'd probably be well advised to write this not using the special notation we use for exponents with trig functions, but rather to write it like this: d dx of secant x cubed. So I haven't taken any derivatives yet, but that's what we mean when we say secant cubed x. We mean take the secant of x and then cube that. That's what that notation means. So if I write it like that, maybe it's a little bit easier to see that the outside function is not the secant function. The outside function is the what? The cubing function, yes. So how do we take the derivative of something cubed? Well, power rule. 3 times that something raised to the second power times the derivative of that something. It's a role reversal. Basically, it's composition of functions, but I'm reversing the order of the composition. Rather than cubing first and then taking the secant, I'm taking the secant first and then cubing. And so the outer function is now the cubing function. Well, now it's just a matter of copying and pasting and using some notation. 3 secant squared x, because that's what that means. Secant x quantity squared is secant squared x. That's how we write it. And now the derivative of secant x, copy and paste this from up here, secant x tangent x. Oh, I guess there's one more step on to clean things up. Secant squared x times secant x, secant cubed x. So 3 secant cubed x tangent x. Started going by thinking, what's the outside function, the outermost function in the composition, and then we multiply by the derivative of what's on the inside.